Hi, in this video we will learn how elementary row operations change the determinant. So here this is the theorem in your book. This is outcome of three different determinant. We have three row operations. Yes, we interchange two different rows. We multiply a row by a constant, non-zero constant, so C is non-zero, or we add a multiple of a row to another row. And here the way determinant of A and determinant of B are related is that if you interchange two rows, your determinant is going to be multiplied by a negative sign. Interchanging two rows, you get a sign, negative sign there. If you change A to B by multiplying a row by constant C, non-zero constant C, then determinant of A is going to be 1 over C of determinant of B. That's the second elementary row operation. It's just something to note here is that we multiply row I by C. What comes out is determinant of A is equal to 1 over C of determinant of B. And if we add a multiple of a row to another row, it's interesting that determinant does not change in that case. So these are the three elementary row operations and the way they change the determinant of a matrix. To have a complete list, this is not only for elementary row operations, but also for elementary column operations. So the above results work for the elementary column operations as well. What do we mean by elementary column operation? Well, you can interchange two column I by column J, or we can multiply column I by a constant K, which K is non-zero, and you can multiply a multiple of not row, a column, so Ci plus K Cj, and well, if you go from A to B by these operations, these are called elementary column operations. What you will get is that, well, the same way, if you interchange two columns, determinant of A would change by a negative sign. If you multiply a column by a K, then you have to divide determinant of a determinant of the resulting matrix by K. And if you add a multiple of determinant of multiple of a column to another column, then determinant stays the same. Well, let's see at least some examples before we move to more details of this thing in other videos. Okay, matrix A is reduced to matrix B through the following elementary row operations, find determinant of A. Okay, so let's do one by one. Determinant of A, well, we change A to a 1 by interchanging two rows, row 1 and row 2, yes. This is what it says. Then our determinant will be multiplied by a negative sign. Then A2 is obtained from A1 by multiplying row 1 by 2. It means that determinant of A1 is going to be 1 over 2 determinant of A2. Well, there were this negative sign. We should bring that. Don't forget that one. So it is there. Then in the third step, we generate A3 by doing this row operation, that multiplying row, adding 3 times row 1 to row 2. We know that determinant doesn't change under this row operation. We have negative 1 over 2. We should bring it from before. And then the next step, we generated A4 by again multiplying, adding negative 1 times R1 to R3. Again, the determinant does not change in this case. We are carrying over that negative 1 over 2. And well, the last step from A4 to B, we multiplied row 2 by basically negative 1. That means that the determinant of A4 is going to be negative 1 times determinant of B. And again, don't forget that negative 1 over 2. And well, the final result is that determinant of A is equal to half of determinant of B. But what is determinant of B? B is an upper triangular matrix. The determinant of upper triangular matrix is product of the entries on the main diagonal. So here we have negative 12. So we have to know these the effect of the elementary row operations and column operations, specifically because we will make or generate new results out of these results.